Hello everybody. Why does the gradient vector tell us the direction of steepest ascent? Or this, you could also say the gradient tells us the direction of maximal increase. So if we have a function on Rn whose output is just one real number, we can create the gradient vector field. This is a completely new map that we interpret as a vector field. And it has a completely different output space. Now that's different from the derivative. The derivative was a map that, if we chose a point, would give us a map with the same output space. It would be a linear map with the same output space as f. Now, what I'm claiming here is that the gradient at a point tells us where to go, the direction to increase the function. How to increase the function f. Okay? And so let's see this. Like if we're at this point here, then the gradient is this little vector here. They scaled it down. Really, it's something longer. And it's telling us that if to increase the function's value, we should move in that direction. That's what the gradient tells us. So if this is the point p equals 2, 1, then the gradient of f at p is the vector 4, 2. We calculated that before. And it's telling us move that way. To increase f, move in direction 4, 2. Okay? That's what it's telling us. Now, why? Well, you can see it's correct, right? Like if we move radially out from the center, we're going to get higher values of this function because we're going to move to circles that have bigger radius, or bigger radius squared. So, 10, 12, 15. We keep increasing the function's value from, what is this? It's at p, it's green, so it's maybe like 5 at p. 2 squared plus 1 squared is 5. So right now at p, here, the function's value is 5. But let's say we want to increase the function value and get to 10. Well, then the best way to do that, we could go over here and then we'd get to 10. But that wasn't the quickest way. What we should do is just go right this direction, and then we'll get to 10 much more quickly. Okay. So now you know what it means. Gradient tells us how to move to increase. And you'll see this in the other plots too. If we're here and this blue, then we're at 0. But what if we want to get to 5? Well, you got to go over here. So the gradient will tell us, go this way. At every point, it'll keep pointing us in the direction increase. If we're here on this purple, then we're at 5. But let's say we want to get to 7.5. The gradient there tells us, go that way. And that's the shortest way to get to 7.5. Of course, we could, go take our time and go over this way, and we'd get to 7.5. But that was not fast. We should go the fastest way and get there quick. Okay, so why does the gradient tell us this? Well, remember that our formula for linear approximation is that we have to add, in order to change the value f of p and to increase it, we need to add something called the derivative, right? But in this case, the derivative of this function is just going to have, partial x1. That's the first, it's just going to be one number at that point, and partial x2. It's going to be one number in this Jacobian matrix. And the formula ends up being v1 times the one number derivative of f with respect to x1 at the point p, plus v2 times the one number derivative of f with respect to x2 at the point p, plus ... all the way to the last input variable whose derivative we take and evaluate it at the point p. And this is a dot product of our movement vector with the gradient of f at the point P. It's just this row, the gradient, or the Jacobian has one row, and we interpret that as a vector, the gradient of f evaluated at the point P. Okay, and so that dot product is, well, the length of v times the length of the gradient vector at P times the cosine of the angle between them. And so let's go look at this. So remember this formula for the dot product of two vectors. And remember what I'm saying here is that if I plug in P, the gradient is a map from over here. The gradient is a map from some point to some vector. And we write, the parentheses mean evaluate the map gradient of f, evaluated at the point P. So then we get a vector. This is just a vector. And so that vector has a length, and we can interpret the dot product in this sense. Now what that means, remember, is that when you have two vectors and they're roughly pointing in the same direction, the dot product will be positive. And it'll be the most positive when the angle theta is 0. When the angle is 0, then v and w are pointing in exactly the same direction. And when the angle is, pi, they're pointing in opposite directions. And so this is really what's going to happen here, is let's look at this again. If we're here and we want to move this way, let's say that's our movement vector v, and then right here is the gradient. You see that little arrow? It's the gradient. Now, let's write gradient of f at P, and this is the point P. So this is literally that vector. So now we can do a dot product between the gradient of f at P, which is that vector, and a movement, our movement v, which could be anything. Now, when will this be a positive number? This number is most positive when v points in the same direction as the gradient. Because of the formula, the length of v times the length of the gradient times the cosine of the angle between them. And so if we want to decrease the function, we should not go this way, we should go the opposite direction of the gradient, because this number will be most negative when we move with velocity v or movement v in the opposite direction of the gradient. And so this is why the gradient works. It's because of the dot product. Because of the formula for v dot w is the length of v times the length of w times the cosine of the angle between them. And so this means that if we move our vector v and we point it in the direction of the gradient, in the same direction, then we will get a maximal increase, because our linear approximation formula was this, and this becomes v dot product grad f at P. This is a vector. I put it in parentheses just to say it's one vector. Okay. And this is the dot. We could write the dot product. Maybe it's better like this. So this is great. In particular, it gives us a really easy way to write the derivative. We used to write the derivative like v1 times the first column of the Jacobian plus v2 times the second column of the Jacobian plus v3, etc. But in the case where the Jacobian has one row, Jacobian with one row, and in only that case, when does the Jacobian have one row? Well, when the output is a real number, when we have a function that has a real number output, that's when the Jacobian has one row. And that's when we do not have something like this, but we instead have something like v1, one number, plus v2, a second column of the Jacobian just has one number, plus 3, 2 times the third column of Jacobian has one number, etc. And this is a dot product of v dot product of some vector. And what is it? Is the gradient of f at that point. So the derivative of f at the point P in direction v can be written as the dot product of the vector v, the movement vector v, with the gradient of f at P. And so you see that each part plays a role. Here's f, and here's P. That means we need to evaluate the gradient vector field at P to get a vector out. Now this is a vector. And our movement still plays a role. It's dot product with the gradient. Okay. And this is sort of why, so the only thing remaining is this d for derivative and this gradient symbol. And that's why people think, oh, the derivative and the gradient, they're the same. But no. For a function, the derivative is a linear map whose output is, again, the same output space. Whereas the gradient is a vector field. It has a different output space. Okay. Excellent. So we see that linear approximation absolutely played a role. The derivative became just a dot product because the Jacobian had one row. Right? What was the Jacobian for this function? It's, the first partial derivative, and then the second column is the second. And you see, because there's one output, there's just one row. Okay, let's look at that again over here. Here's another function. What's its Jacobian? Well, partial x gives 2x. Partial y gives 2y. Partial z minus 2z. And you see there's one row. One row Jacobian. And so that's why we can now write the derivative, only in this case, as a dot product with the gradient.